So in chapter 15, we'll be looking at three-dimensional shapes of molecules. Organic compounds can have different versions, even though they're connected together differently. Just like we have a left hand and a right hand, some organic compounds can have handedness to them as well. We see the seashell here. They only spiral in one direction, which is characteristic to that seashell. When we're looking at isomers, they can be defined as having the same molecular formula, but being a different compound. We've run into constitutional isomers, which have the same formula, but are connected differently. And in this chapter, we're going to look at stereoisomers, which have the same formula, they're connected the same, but in 3D, they are arranged a little bit differently. And the first pair that we're looking at with the OH and the bromine compounds, that first one has the OH and the Br that are both up or wedged. So these are on the same side as each other. And on the second compound here, the OH and the Br are on opposite sides as each other. So the OH is dash and the Br is wedge, where OH is pointing back. But those have the same formula, they're connected the same, it's just in 3D space they're arranged a little bit differently. And these two alkenes here, these groups are both on the same side of the alkene. And these are on opposite sides if we look at the tops and the bottoms there. So in our first practice problem, we can look at each pair of compounds and determine if they are constitutional isomers, the same, or stereoisomers. If I look at the first compound, I'm going to count up the number of carbons. This one has 7. And that one has 7. There's no functional groups coming off of them. They're both arranged the same way. And if I'm naming them, they're both going to be heptane. So these are identical. In the second set, I have 5 carbons here. There are 2, 4, 6, 8, 9, 10 hydrogens, and then 1 oxygen. The second compound has 1, 2, 3, 4, 5. Hydrogens are 3, 6, 7, 8, 9, 10, and 1 oxygen. These compounds here in the middle have the same formula, but they're put together differently. So these are constitutional isomers. And in the last one here, we have 1, 2, 3, 4, 5. H is 3, 6, 7, 8, 9, 10. This one is also H10. The formula is the same. They both have an alkene coming off of the second carbon, but in this one, the groups are on opposite sides of each other, and these are on the same side. So these are stereoisomers. So molecules can have a mirror image of each other, just like our hands are mirror images of each other. A pair of molecules can be identical or they can be different. So if you look at your left hand with your palm facing up and you look at your right hand with your palm facing up, they mirror each other once you put them palm to palm. So they're mirror images of each other, but they're non-superimposable. That means that you cannot stack them in any ways on top of each other where they match up perfectly. If we look at this pair of socks, those are mirror images of each other as well, but I can lay one sock on top of the other one, and that makes it superimposable. The twins that are shown in the image here are mirror images of each other. However, one is left-handed and one is right-handed. Superimposable means that all of these parts can be stacked together, and that's all the parts of the molecule. So that would mean that your hand has to have all of the parts stackable as well. So you might be able to stack your pinkies on top of each other, but the rest of the fingers on your hands don't match that. And then non-superimposable means that the mirror images cannot be stacked. So we're going to look at these compounds and classify each of them as being chiral or achiral. So chiral means that it has handedness and no symmetry. And achiral means that there's usually symmetry. There's no handedness. So if I look at a group of nails here, I can draw a symmetric axis down the middle. So these are achiral. A screw, though, I can't cut that in half and have one side match the other because of that spiral down the middle. So this is chiral. A glove goes on top of a hand, which is chiral. So this is also chiral. And this pencil happens to be achiral. So if something is superimposable, this is achiral. And if it's non-superimposable, it's chiral. There's two water molecules here, and there's a mirror plane shown in between them, and one of those water molecules mirrors the other one. And if I stack them up next to each other, the bonds and the lines in these molecules align, so the molecules are aligned. Which means that H2O, or water, is achiral. So if there's an axis that we can draw of symmetry, it's going to be achiral. In this compound here, we have two hydrogens, chlorine, which is in green, and the bromine, which is that orangey color. We're looking at the two compounds. They are mirror images of each other. And if I rotate the molecules to align the bonds, these also align. So CH2BrCl is achiral. If I change one of those hydrogens and replace it with a fluorine, I have the mirror images that are drawn here. So we have A and B, and I look at the next drawing over, I can get the hydrogens to align, the yellow atoms, which are the fluorine, to align, but the other two don't align. So this is not superimposable. Those don't align. So CH_BrClF is chiral. And A and B happen to be enantiomers of each other. An enantiomer is a mirror image that is not superimposable on its mirror image. So your hands are mirror images of each other that are non-superimposable. Your hands are enantiomers. So your hands are also chiral. In order for a compound to be chiral, it has to have a tetrahedral carbon, and it must have 4 different groups attached. So when locating a chirality center, we want to make sure we find a carbon that is tetrahedral, which means it only has single carbon-carbon bonds, or carbon other atom bonds, and it has to have 4 different groups attached to it. So this C right here with the Br, Cl, I, and F is a chirality center. And on that one carbon, there's a Br, an I, an F, and a Cl. So those are 4 different groups. The carbon in the middle of this compound is also a chirality center, which I'm just going to mark with an asterisk. That's the common convention for marking chiral centers. This compound, if we do the nomenclature for it, this is 3-bromohexane. And on that particular carbon, we have a hydrogen. It's attached to a CH2CH3. And the other group that it's attached to is a Br and a CH2CH2CH3. And this is different from the other group prior because if you want to think of it in terms of a substituent, this is an ethyl group and this is a propyl group. Those are different groups, so that makes that carbon that it's bonded to a chirality center. So the problem here is to locate the chirality center in each drug. Penicillamine is used to treat Wilson's disease, which is a genetic disorder that leads to a buildup of copper in the liver, kidneys, and the brain. Albuterol, which is used for asthma, is a bronchodilator. It widens the air passages. If we're looking for our chiral compounds, the first carbon is not a chiral center because it's sp2. So this does not fit the criteria for being a chiral carbon. If I look at the next C, there's an H, the C double bond OH, NH2, and this other group down here. So this is a chiral center. I look at this carbon, I have a C, the group above, an SH, and two CH3s. This makes this also not a chiral center. So the only one is that middle carbon there. And the reason that penicillamine doesn't have chiral center with the SH is because there's two CH3 groups there, and those are the same. In albuterol, we're going to rule out any CH2s, any carbon-carbon double bond, so anything in that benzene ring is out. Here's another CH2. This carbon right here has three CH3 groups on it. Those are equivalent, so each of those are out, as are the CH3 groups. So our only chiral carbon is this one right here that has the OH attached, this carbon chain, the benzene ring, and the hydrogen. Compounds can have two chiral centers or hundreds of chiral centers. Tartaric acid is isolated from grapes, and we often see this in cream of tartar, which is used in baking. If you're whipping up egg whites, you want to use cream of tartar to stabilize them so that it doesn't break. The other structure that we see is that of ephedrine, which is a bronchodilator and also a decongestant. Ephedrine is isolated from the herb mahuang, and this can be used in Chinese medicine to treat respiratory ailments. Each of those have two chirality centers. There's one right here, one here, and even though both of these carbons here have the same groups attached, so each of them have the same four groups attached, but they're connected differently. So the first carbon has an H, a C double bond OH, an OH, and another C. And this C has a C, an OH, a C double bond OH, and an H. So those are four different groups. Ephedrine also has two chiral carbons here. So ephedrine also used to be a popular drug to promote weight loss and enhance athletic performance, but now it's been linked to episodes of sudden death, heart attack, and stroke. In this practice problem, we're going to locate the chirality center in each of these molecules. So if you can recall, we can rule out any sp2, CH2s, and CH3s. So on this first one, this is 2-chlorobutane. This is our only chiral center here. It's attached to a Cl, a CH2, and then the CH2CH3, along with the hydrogen. Here's my chiral center here. There's a methyl group, a Br, an H, and the benzene ring. This one here has no chiral center. All right, in this next problem, we're going to locate the chiral center in fluoxetine, which is also known as Prozac. So a CF3 has 3F, so that one's not going to be a chiral center. CH3 will not be, or this CH2CH2. So we're looking at this compound here, which has an O phenyl group. Here's a phenyl group, and then a CH2, and the H here. So this is my chiral center. So any molecule that has just one chirality center is a chiral compound. So here we're asked to draw the enantiomer pair of the following. If I'm going to draw the enantiomer pair, I have to draw mirror images of the same compound. So this compound has no stereochemistry as it's drawn. Okay, so I'm going to draw an enantiomer pair. I have the carbon skeleton. I'm going to wedge my alcohol and dash my hydrogen. So this is one of the compounds. If I'm drawing the pair, you draw the mirror image. So my OH is wedged and the hydrogen is dashed. Another way that you can draw the enantiomer is to just draw the same carbon backbone, but take the opposite stereochemistry. If your OH is wedged in the first drawing, it becomes dashed in the second drawing. Your hydrogen is dashed, now it becomes wedged. So these two are enantiomers. Here's another practice problem. Although fresh human sweat has no odor, enzymes in skin bacteria form a variety of compounds with distinctive pungent odors. The two enantiomers of 3-methyl-3-sulfonyl-1-hexanol, which smell somewhat differently, contribute to the characteristic foul smell of sweat. Locate the chirality center and draw both enantiomers. So no CH2s, CH3s can be a chiral center. The only one here is that one. And that drawing as it is has no stereochemistry to it because it's just drawn all flat. So we need to include stereochemistry. So I can wedge the methyl group and dash the SH or the thiol. And then do the opposite for the enantiomer. Alternatively, you can just draw the mirror plane and draw the mirror image of that. Okay, so is C1 a chirality center? We're looking at methyl cyclopentane. We have a carbon here. If I look at the C1, the groups that I have are H, CH3, which are different, and then you have to work your way around the ring. So if I call this A, these are chemically equivalent. So is B. So this is not chiral. So we have those identical groups there. If I look at 3-methylcyclohexene at C3, or what the book is calling C3, there's an H, a CH3. This A is a CH2, this one is a CH. So these are different. C3 is a chirality center. There are some medicinal enantiomers of importance. Thalidomide. So this is a drug that was used for morning sickness in pregnant women between 1959 and 1962. They were sold as an enantiomer mixture. So these were sold as an enantiomer mixture. One enantiomer was used for anti-nausea, which is why they were giving it to pregnant women. However, the other enantiomer, because it binds differently in the biological systems, caused catastrophic birth defects. So the anti-nausea drug had this group being wedged. And this one over here, when it's wedged and this is the enantiomer, this is the teratogen. So a teratogen is a term that is used for compounds that cause catastrophic birth defects. This drug is no longer used for the treatment of morning sickness. So chiral drugs are important. One enantiomer can be effective while the other is not. So we saw an example of that in the last slide, except it had terrible side effects. So when we're looking at chiral drugs, one enantiomer is going to fit just right in the binding pocket. So in this example of phenylalanine, which is an amino acid, it can fit into a chiral receptor in a certain way where we can think of it as box, triangle, and then oval. But if you have the mirror image of that, when it's turned around, it's not going to fit the same way in all three of the categories. You might just get it to fit in the one spot right here. So this is why one enantiomer can be effective while the other enantiomer of a drug is ineffective. And we're looking at different chiral pain relievers. Ibuprofen in the A version is the active anti-inflammatory agent, while the B is the inactive enantiomer. It is sold as a racemic mixture. So racemic means that there's both enantiomers present. The reason that they can sell this one as a mixture is because B can slowly convert to A. So there's not going to be any detrimental side effects here. Naproxen, which is also sold as Aleve, has an A form that is active, and B that is a liver toxin. So naproxen is sold only as one enantiomer. And we have a practice problem. Propranolol, which is under the trade name Inderal, is used in the treatment of high blood pressure and heart disease. So we're asked to locate the chirality center and then draw both enantiomers. And one of these is biologically active. So for our chirality center, we're looking for an sp3 carbon and 4 different groups. So we can rule out any oxygens because it's just going to be carbons that are chiral, any CH2s, any sp2 carbons. So I'll start here, and this looks like it could be one, but I have 2 CH3 groups which are the same, so that one is not a chiral center. The N is not one. This is a CH2. This one is also a CH2. So we're looking at this guy has an OH, a C to O, and then C to N. So this is my chiral center. So when I go to draw the enantiomers, we're just going to give some stereochemistry at that one chiral center. So I'll make the oxygen here wedged. Okay, so there's one enantiomer. And if you like to draw the literal mirror image, we can do that. Okay, so those are the mirror images. For me, I like to draw just the same thing with the opposite stereochemistry. That one is easier for my brain to process. But if you like drawing the literal mirror image, then by all means, please do that. So L-DOPA was isolated from seeds of the broad bean Vicia faba. This is the drug of choice for Parkinson's disease. It can be made in the lab. So L-DOPA is transported to the brain by the bloodstream, and it can be converted to dopamine in the brain. So we have L-DOPA, which has this chiral center here. So that's L-DOPA, which is active against Parkinson's, and then D-DOPA is responsible for the undesired side effects. So dopamine affects brain processes that control movement and emotions. So proper dopamine levels are needed to maintain a person's mental and physical health. When our dopamine levels drop, dopamine is affecting our brain processes that control emotions and movement. So we can see the dopamine release here and the different receptors. Having proper levels of dopamine are needed in order for us to maintain mental and physical health. If we see a drop in dopamine, this is going to result in the loss of motor control, which is symptomatic of Parkinson's disease. But dopamine cannot be given as a drug, and that is because it cannot cross the blood-brain barrier. If a compound has only one chiral center, then there are two structures possible, or two stereoisomers. And the number of stereoisomers is going to be dependent on how many chiral centers you have. So if we have more chiral centers, there are going to be more stereoisomers possible. And there's a formula for that where it's 2 to the n, and n equals the number of chiral centers. So if I had 2 chiral centers, I would use 2 squared, which would equal 4 possible stereoisomers. So in these first two here, we can see the different stereoisomers. On A, the NH2 here is on the left side, whereas on B, it's on the right side. And the OH is on the right side, and the OH in B is on the left side. So these two happen to be mirror images of each other, so they are called enantiomers. And then we have C and D. Both of those NH2 and OH groups are on the right side in one structure, and on D it's on the left. These are also enantiomers. In all four of these, they each have 2 chiral centers, so we have 4 stereoisomers possible. The relationship between A and B and then C and D are that they are enantiomers, but A also has a relationship to D, and that is a diastereomer. These are defined as stereoisomers that are not mirror images of each other. So in order to be a diastereomer, you must have at least 2 chiral centers, and they cannot be enantiomers of each other. So A and B are mirror images of each other, so they are not diastereomers. But in A and C, if we look at those, there is an NH2 on the left side in A and an NH2 on the right side in C, so those are mirror images of each other. But the second part where the OHs are, those are on the same side. So they're not enantiomers, these are diastereomers of each other. And B and D are also diastereomers. So again, diastereomers are compounds that are stereoisomers and not mirror images of each other. So they have the same formula, they're connected the same, but they're different in 3D space so that they are not enantiomers of each other. Isomers are different compounds with the same molecular formula. We've split them up into constitutional isomers, where they have the same formula, but they're connected different. Stereoisomers are connected the same, but are different in 3D space. And then within the stereoisomer, you have enantiomers, which are mirror images, and then diastereomers, which are not mirror images. And with the diastereomer, you need at least 2 chiral centers. So if we look at this problem here, consider the structures below labeled A through C. How are these related to each other? So if I'm looking at A and B, the formula is the same. If I drew a mirror axis down here, they don't mirror each other. The OH on one side is dashed and it's wedged over here. So those are not mirror images of each other. There's 2 chiral centers. So for A, these are diastereomers. In B, we're looking at A and C. A and then C, those are mirror images of each other. So the OH mirrors the other OH where it's wedged. And then the second one that's connected to the ethyl group is also mirrored there. So these are mirror images, these are enantiomers of each other. For C, we're looking at B and C. These ones are not mirror images of each other either, because this mirrors this guy in the way that it's drawn, but this one doesn't. So these are diastereomers. If we look at actual compounds that have enantiomers in nature, so you can tell by your sense of smell that these compounds are different despite them being enantiomers of each other. So research suggests that the odor of a particular molecule is determined more by its shape than by the presence of a functional group, which is why we have the structure here. This is carvone, which is enantiomer A. Those are caraway seeds. And the mirror image is compound B, which is also called carvone. This one has the smell of spearmint leaves, which is very different from that of rye bread. The compound is the same except for the way that our body perceives them because their shape is a little bit different. So the lining of the olfactory bulb in the nasal passages is going to be sending messages to our brain. And that will tell us that it's caraway seeds versus the carvone or the spearmint leaves.